Okay, hi, Mr. Kwang here. Let's talk about lecture 3b. We will be talking about good abstraction. Okay, what exactly do we mean by good abstraction? So let's look at the details of this series of lecture. Okay, so good for this lecture, right? We're going to talk about what abstraction means, and so understand its advantages, and so to understand key approaches to problem solving. Right? What's going on? Essentially, for abstraction, right, what you're trying to do is to manage complexity. Okay, and so you need to divide and conquer, right? So basically, you will see how we can break down problems into simpler chunks, and then we can address each chunk on its own first before we combine them back together again. All right. So basically, what we're trying to do here is that when we have a problem, we don't just look at the problem as a whole. We try to break it down into subtasks, right? So there's subproblem 1, subproblem 2, and of course from there we can further on divide it to maybe even subproblem. Okay, so we try to break it down as much as we can, because when we do this, we are able to resolve smaller problems more easily than when we're dealing with a big problem. So we are just solving each part one by one, and then combining them to get a solution. Right? So when we talk about abstraction, we are taking a problem. We are not just looking at the primitives that are involved in the problem. That means we are not looking at the variables, the kind of strings we use, integers we use, etc., etc. But we are looking at how we can break it down into instead of just using one function to solve, we want to break it down to use multiple smaller functions to address the issue. Okay, so we make use of abstractions to do this. Okay, so what makes a good abstraction, right? Okay, so these are some of the points that's required for a good abstraction. There are 7 points that we have highlighted, and then we'll go through them one by one right now. Okay, first one, good abstraction makes it more natural to think about tasks and subtasks. Okay, what do we mean by this? Let's look at the next one. Okay, when we want to build a new house, do we think about the bricks directly? We could, because we would start to count, oh, to build this entire house I need a certain number of bricks. But I realize it's very hard to estimate the number of bricks you need if you do not know any details of the house. So it makes more sense to break down this problem into smaller parts. Like for example, when I want to build a house, the first question I ask myself, what kind of house do I want to build? Do I want to build a house, 2-level house, or 1-level house, or do I want to build one with a rustic theme or an industrial theme? And then once we have done that, we can start to break down how many rooms we want for that house. Okay, so we break it down the rooms first, and then from each room we can now start to think about how many bricks we need. Okay, so this is a more intuitive way of solving the problem, because for us, it's not intuitive for us to, when we think about house, to think about the bricks, number of bricks directly first. We think about what we want to build, the different sections of the house first. Alright, so in this same vein of thought, okay, this is essentially dividing and conquer. In this same vein of thought, right, when we want to write a program, we don't think about what are the primitives that we need to use first. We think of how we can break down our program into smaller functions that we can use. And then from the functions, we start to think about the primitives that we want to bring in. Okay, so this is essentially dividing and conquering. Okay, next, it makes programs easier to understand. Alright, so let's look at this function here. Compare the top one. The top one, right, you have defined clearly a sum of squares function, a square function, and then your hypotenuse function, which makes use of the sum of squares function over here. Okay, you can see that basically, right, this way of working is that if you look at this sum of squares is defined outside here, but then this sum of squares is also dependent on the square function that is in here as well. Alright, so you may think that this is quite cumbersome, but why can't you write it at the bottom like this, where you just basically mush everything into one? You can, but then in terms of making sure your code is easy to understand, like for example, like 6 months down the road, you look at your code again, will you be able to understand this very, very quickly? Will someone else be able to understand your code very easily as well? Like for some people, right, they think of square as just a power 2, but in this case, you're thinking of a times a. Okay, so this is not so clear, but then to the reader, when he sees sum of squares, right, it's very clear for him what you're doing. Okay, next, it captures common patterns. Okay, what do we mean by this? Okay, let's look at this statement here. So you have your this is your spending for each month based on your income. Okay, so you have my finances equals to then food. Then you can see that, oh, this is basically give you a string for food, then converting a number into a string and then put it in together. So you get a combined statement for of your spending. But you notice something that always comes out. In this case, right, there's this always 1,000, 1,000, 1,000, 1,000 here. Okay, what exactly is happening here? Because right now, right, you can see that this is actually your income for that month. Alright? So imagine if you want to, if let's say 6 months down the road, your pay has increased to 1,005. Alright? If you want to update this, you have to update every single one of them. Every single 1,000, 1,000, 1,000, you change for them. Alright? So if in this case, right, when you use a function that calls in that calls for the argument of the salary to go in, okay, then you can the body of a function itself, right, you can just call on salary. Okay, so in this case, right, I can use this function for I can use this function on a salary of $1,000. If down the road I got a pay increment, then my salary could be 1,002 or 1,005. This function will adapt itself accordingly, right? Because you have not hard coded the $1,000 into the function itself. Okay, next, it allows for the code to be reused. Alright, so this one is quite useful, especially you're working on the massive project. Okay, what do we mean by that? Alright, so let's say we define a square function. Okay, define square, then returns x times x. Okay, so for this one, right, just now we use the square function to find the hypotenuse. But if you think about it, it's also useful to calculate other things as well. For example, the area of a circle. So if I were to write a function to determine area of circle, right, given its radius, we know that this equation is area equals to pi r square. So I define pi as 3.14159, and then I write the function define area of circle r. So I just return pi times square r. I don't have to write return pi times r. You can do that, but then the thing is that you have already written the square function. You can use it again here. Okay, so there's no need to replicate your work. Okay, next, it hides the implementation details. Okay, what do we mean by that? Okay, remember we talked about this, we have an area of circle generator. So if let's say you are the one who wrote the function, then of course you know what's inside this function. But to the end user, right, it's not important for him to know what this function is. To another program that's calling on this function, right, it's not important for the program to know what's inside this area of circle generator. Okay. Right, next, then it separates specification from implementation. It's similar to just now what we have. So remember we mentioned in 3a that functional abstraction is a black box. Okay, so you don't need to know how a car works to drive it. Okay, what this means is that if you just imagine if I have a function called car, okay, basically you just need to drive the car. You don't have to know how the car works. Okay, you don't need to know what's going on inside the car. You just need to know that you use the car to get from point A to point B, right? So basically, we're trying to separate specification from implementation. Okay, so specification is what it should do. Implementation is how it does it. So this is like, for example, let's say you are a client. You are looking for someone to program something for you. Then basically you tell your coder, say, oh, I want my code to be able to do this. I want the code to take an input and do this. Okay, then it's up to the coder to implement this. You don't have to know what's happening behind the scenes. Okay, you just need to know that when you get the end product, right, you run it, it works correctly for you. Okay, so that's what I mean by separating specification from implementation. Okay, yep. And next, it makes debugging, which is fixing errors, easier. Okay, for this, let's look at the example here. Where is the bug? Which code is easier to check? Okay, so I'm going to flash two codes for you on the screen. Okay, actually I can show you one. Okay, just look at this one first. Okay, so this one I have written square root of a plus a times b plus b. Alright, then versus the other version. Okay, so this one is I have a square function, I have a sum of squares function, okay, and then I have a hypotenuse function. Alright, I think this one you can spot the error quite easily. Let me just backtrack to the previous one, hypotenuse, right? So you realize that now this is actually wrong as well, but it's a bit harder to spot error because now this you have to look at each line within one function to find the error. In this case, the error here is actually this one here. It should be a times a plus b times b, correct? Okay, but it'll be easier to spot it on this one here. Sum of squares, okay, so look at sum of squares function. This is correct, square x plus square y. And then hypotenuse is the square root of sum of squares a and b, which is fine. But then now you can see clearly in your square function this is wrong because square should be return x power 2 or just x times x. So this is easier for you to spot. Okay, so this is basically what we have. Why we need to make use of good abstraction. I think for me personally, I feel that for allowing the code to be reused is one of the most useful feature here. So this is something you need to take into account when you are writing your functions. Okay, we'll stop here for this part. Then we will talk about the next. We'll show you a real life example in the next video.